And so today we are going to get through the applications of commutators. So we defined them, but we're going to see how commutators can be used to get useful moves on our permutation puzzles. So, after today, it's likely that if you've been playing around with Rubik's Cube, then after the stuff we talk about today, you'll probably have a good foundation to be able to just solve it on your own. And then you might ask, well, then why is the Rubik's Cube section not finished until chapter 18 or chapter 19 and chapter 20? And that's just because there's a couple of different aspects to Rubik's Cube. There's coming up with a solution strategy, so the moves we need to solve it, and that's going to be basically a product of today's class and next day's class. But then there's the flip side is being able to determine, given an arbitrary reassembling of the cube, whether it's solvable or not. And so the solvability criteria is another question, and that requires a bit more machinery. But being able to solve it, if it is solvable, will be done with today's material and Wednesday's material. So let's have a look at where we are so far. We introduced this idea of a commutator, and all it is just a way of taking two moves, in this case, two elements of our group, and just multiplying the two of them and then multiplying them with their inverses as well. So it's a element of the form G inverse H inverse. And we use the square bracket notation with the comma between them to denote their commutator. And it turns out that these things actually have particular use in studying groups that are non-commutative, and that's going to be most of our permutation puzzles. And in fact, they're very useful for creating certain elements in the group or certain permutations. And in our case, that translates to building puzzle moves. So we did some examples where we just computed the commutators. And now we were just getting started with how can we use a commutator? How can we use this product of these two moves in this way? We're going to think of these as permutations now. So commutators, permutations. How can we think of, when we take a commutator of permutations, how can we think of that as building something useful for us? Well, it first starts with figuring out for a given permutation, what are the two sets related to it, the fixed set and the move set. So the fixed set are all the things that it doesn't touch, it leaves where they are, and the move set are all the things that get moved by the permutation. The move set is also called the support. Maybe I should make a note of that. The move set, also called the support of alpha. And we're going to call it the move set just in contrast to the fixed set. But in other literature, if you do look up permutations and you're reading about them, then you might see that they call this thing the support. And it's really, that sort of conjures up the idea that this is a permutation. So let's scroll down to our example down here. This permutation alpha, the support is just all the numbers that make it up: 1, 5, 3, 9, 4, 11. In other words, those are just what we call the move set. And I just want to point out that there was an error in my list. 5, for some reason, I put it in the fixed set, but 5 should have been in the move set. So that 5 should be down here. Put a 5, comma, and we'll get rid of it from up there. Okay, so then the next thing we want to do is talk about, given a set of objects, so these are some of the numbers that are in the set being permuted, we want to apply a permutation to that. And so that was this material up here about, given a set A, we're going to define alpha times A. So I've written alpha in front of the A. And that is just apply alpha as a permutation. It is a function to all the elements in A. And so we call that the image of A under alpha. It's just a shorthand notation for, if we just restrict our domain of our permutation alpha to just those things in A, what happens? What does alpha do to those things? And since alpha is a permutation, it'll take all those elements of A to other elements in the set of 1 through n. And so the size of the image of A under alpha is precisely the same as the size of the set A. This was our example down here where we started with this set of numbers, 1, 3, 5, 7, 9, 11. That's just an arbitrary collection of numbers. Just for the example, I just wrote down 6 numbers. And then alpha of A is just alpha applied to those 6 numbers, which returns these 6 numbers. And so this is just the image. If we start with the numbers 1, 3, 5, 7, 9, 11, and we apply alpha to those numbers, these are what results. The way we're going to use this is we're going to think of things as follows. We're going to say, suppose I got a puzzle, and suppose I do a move sequence on it called alpha. Then what does that move sequence do to the pieces in positions 1, 3, 5, 7, 9, and 11? Where do those pieces get moved to? So those pieces got moved to 5, 9, 3, 7, 1, and 4. So that's how we're going to use it. We're going to use it to, given a move sequence, alpha of A is just where all those pieces that are sitting in locations of A, where they get moved to. Okay, so now we're going to get to the heart of the matter. When is a commutator of alpha and beta close to the identity? And by close to the identity, I just mean it only moves a small number of things. That's what it means by close to the identity. It means the move set of it is very small. When is the commutator of alpha and beta small? When is it close to the identity? When's that permutation close to the identity? Whenever it is, that's a good move sequence because it only moves a few pieces. So let's have a look at this diagram. And what I'm doing is I'm just thinking of these as sort of 2 like turntables, if you will. And alpha is just like spinning the left turntable clockwise, and beta is spinning the right turntable counterclockwise. And those are just all the objects that we have being permuted that are listed all here. The ones that are being moved by alpha and beta. And what we want to do with this diagram is we just want to try to figure out what all of these pieces are in each of these little blobs. So the first thing we're going to do is we're going to just notice that, let's name this piece right here. So this is our intersection. Maybe I'll choose a different color. I'll choose black because I'm writing green on green. So what are the pieces that are sitting here? Well, those are going to be all the pieces that were moved by alpha, but they're also all the pieces that are moved by beta. And if I imagine spinning alpha and spinning beta, then the intersection of those 2 sets, like this is a Venn diagram here, the intersection of those 2 sets, these are all the things that are moved by alpha, intersected with all the things that are moved by beta. Maybe to complete this diagram, this set here is just the move set of alpha. I'm just imagining that whole circle there, everything in it like a Venn diagram. That's all the things moved by alpha. These are all the pieces that beta moves. And so their intersection is the things that are moved by alpha and beta. And just for shorthand of notation, we're going to denote this by move of alpha comma beta. So that's just a shorthand. So I don't always have to write move alpha intersect move beta. I'll just write move alpha comma beta, and I'll read it as this is the move set of alpha and beta. So all the things that alpha moves and all the things that beta move all together. What else do we have? Well, let's just think about what's going on with pieces in these other sets. Okay, so what is a piece here going to do? So now what I want to do is I want to track. If I do alpha, beta, alpha inverse, beta inverse, where do all these pieces move? So what does the commutator alpha beta, which is alpha beta alpha inverse beta inverse, move? And I'm going to claim that the only things that it moves are the things in the green sections. Those are the only pieces that get moved, are the things in the green sections. So let's see why. Let's pick an object here. So suppose that's, maybe it's just like a sticker on the Rubik's Cube or one of the tiles on the oval track puzzle. We'll just pick it. Suppose it lives here in this set. Then what alpha does is it moves it down here. So there it is. So we do an alpha move, that's a rotation of that turntable. It brings that piece down into that set. And then what I do is I do a beta move. So a beta move will then push it over here. Because again, beta is a rotation of the turntable. And then I will do an alpha inverse move. So I rotate the alpha turntable in the opposite direction. But since this piece now down here is no longer on the alpha turntable, alpha doesn't do anything to it. So either does alpha inverse. So now I've rotated the alpha turntable backwards in the counterclockwise direction. And then the very last move is to rotate the beta inverse back in the opposite direction. So when I do that, it now comes back here and lands in this spot. And that's true of everything in that green blob on the alpha side, that left-hand green blob. All of those pieces slide into the middle. So what we have is that this entire green blob, maybe I'll do this in the pink, it moves there under this commutator. So now let's do the same thing with an arbitrary piece in here. Where does a piece in the move alpha intersect move beta go? Well, that's under alpha. So again, we got to keep our eyes on what we're doing. This is the move we're doing. Under alpha, it moves over here. And then I do a beta move that rotates the beta turntable. And then I rotate the alpha inverse move. So that means it comes back here. So that was our alpha move. Here's our alpha inverse. And then we do a beta inverse move. So it lands over here. And so every piece that's in that middle section, after we do alpha, beta inverse, beta inverse, it all lands in the right-hand portion of this diagram. So all of these things move here. So under alpha, beta, commutator, these are where these things are going. And now what about that last piece? It might indicate that if these were the only things that move, then this whole piece should end up moving over to the other side of the diagram and becoming that left-hand blob. And so let's just see if this is the case. So we've got a piece here, and we do an alpha move that leaves it untouched. Then we do a beta move that brings it down here. So that's our beta move. And then we do an alpha inverse move that brings it up here. And then we do a beta inverse move, but now it's already off the beta inverse or the beta turntable. So it stays here, which means all of these pieces eventually end up over here under the commutator alpha beta. So we'll get rid of this intermediate stuff. And so that's our diagram, is that every piece in each of these blobs, the green blobs, moves around in this way. So what about a piece that isn't in any of these green blobs? So let's look at some other pieces, maybe a piece down here. So other pieces. What happens with those? Well, when I move alpha, any one of these pieces is just going to sort of rotate around. It's not going to land back into the intersection because the stuff that alpha moves into the intersection is precisely that green blob on the left. So under alpha, these move over here. Then we do a beta move that doesn't touch any of these things. Then we do an alpha inverse move, they come back. And then we do a beta inverse move, it doesn't touch those. So all of these other pieces, they just remain where they are in the end. They just sort of rotate back and forth, but they never get caught up in the mix because they're on the alpha side that never gets moved into the beta, so they never get touched by the beta move. And similarly, there's going to be other pieces over here and those other pieces remain. They don't get mixed up either. So what we have is when I do a commutator, I immediately can see what pieces are going to get moved by it. It's going to be all the pieces in the intersection. So all those pieces that are moved by both alpha and beta, or the pieces in the locations that are moved by alpha and beta. And these other two sets hanging on the edges. And so what are these other two sets? Let's see what they are. Well, any piece in here was precisely a piece that when you applied alpha to it, took you into the intersection. So if I call this like piece X, then its property is that alpha of X is an element of the intersection of alpha and beta. So what does that mean? That means that X is in alpha inverse of the move set of alpha beta. Where, again, what is the notation I'm using here? This is permutation sitting in front of a set. That's the notation we used above. That was our image of the move set under alpha inverse. And so that's what this set is here. This is alpha inverse of all of the locations that are moved by alpha and beta. Okay, so that's this set. Similarly, these pieces are precisely those things that beta moves into the intersection. Or another way to say that is those are the pieces obtained by taking the intersection and applying a beta inverse move, rotating beta in the opposite direction. So that might be easier to see from this diagram, that if I take that green blob in the intersection and I just do a beta inverse, rotate the beta turntable in the opposite direction, that lands on top of this green set. So that's beta inverse of the move set of alpha and beta. And those three blobs are the only three blobs that get moved by the commutator. And so that's what we've written down here at the very bottom, is that the move set of the commutator, so this thing here, is at most the three green blobs. What's moved by the commutator? At most, it's these three green blobs. Nothing else, anything that's not in these green blobs will not get moved. And so that's what we've written down below, is that the move set of the commutator is the intersection. This thing, which is alpha inverse applied to the intersection, or taking alpha and rotating it in the opposite direction, doing an alpha inverse and finding out what that other blob is, and then beta inverse of that move set. Now I like to read this as follows. The move set of the commutator is the things moved by both alpha and beta. The things alpha moves to positions moved by both alpha and beta. So that's a bit of a mouthful, and we'll see what it means in a second. And then this one is the things beta moves to positions moved by both alpha and beta. Okay, so that I'm just giving sort of names for each of these green blobs. The things in the middle are just all those positions that were moved by alpha and beta. The thing on the left-hand side, that blob on the upper left, those are precisely the things that when you do an alpha move, they move into the positions that have been moved by both alpha and beta. And the blob on the right are all of those positions that when you do a beta move, they move into the intersection, or the places that have been moved by both alpha and beta. Okay, so that gives us the ability to figure out exactly which pieces are being moved under a commutator. And now what I'm going to do is I'm just going to provide a proof of this picture. So what we've done so far is we've just sort of done like a hand wavy argument. I've drawn a diagram and I've imagined turntables moving, and I captured this idea that the move set is precisely going to be contained in the union of these three green blobs. Now we can give a more rigorous argument for this, just to see that this is all really the case. If you're following at this point along with the sort of hand wavy one, that's perfect, because that's the hand wavy one is fine. This is what we're going to need for the puzzle. If we really want to put this on a firm foundation and avoid the hand waviness, then this is what we're going to do next. We're going to put it under firm foundation here. So what do we have? Well, what I want to do is I want to try to figure out what are all the pieces that alpha, beta, the commutator alpha, beta moves. What are all the things? Can something in the blob not be moved? Yeah, everything not in the green blobs are going to eventually return to where they started from. That's this whole business about the other pieces. So if you're not in one of those green blobs, then you will move a little bit. Like if you're on the alpha turntable, you'll rotate and then you'll rotate back, but you never get caught up in the mix. So only those pieces when you rotate alpha that land in the intersection that then beta rotates, those are just that upper left green blob. Those are the pieces that alpha moves into the problem area. But every other piece that's not in any of those green blobs, they just rock back and forth on the respective turntables. Why do we say most? Because I haven't actually stated that these are disjoint. So our green blobs could look like this. Right? They could all overlap. In which case, the things that get moved, maybe that thing in the intersection of all of those, it ultimately never gets moved in the end. So that's why I'm saying at most. There is a bit of subtlety in here. And of course, if I'm going to claim that there's a bit of subtlety in here, then there'll probably be some exercise on the assignment at some point, which has you get across, given an example, verify that it's actually not the full union. There's something that actually doesn't get moved. It's in these one of these sets, but in the end it doesn't get moved. So it has to do with the fact that there could be intersections. Where the item should be landed if we do an alpha. Yeah, so absolutely I can do that again. Let's think about what's going on with each of these pieces. So I'm just going to let an arbitrary piece be, something like this. So I'm in one of these other pieces. So if I do an alpha move, that's just a rotation in this direction. And then it lands somewhere. I guess if we're being precise in that I've drawn all the pieces, it's either in one of these three green blobs. So then it rotates around, it lands in here maybe. And then I do a beta move. So because it's not on the beta turntable, when I do a beta move, it doesn't touch it. And then I do an alpha inverse move. So alpha inverse would go in the opposite direction of alpha. So then it just comes back to where it started. And then we do a beta inverse move. So we're going to get to the cube, but we can certainly do it here. Like, for example, let me just bring it so that the red face is front. There we go. We can see the red face now. Let's say our this is our alpha move. That's one turntable. And this is our beta move. That's our other turntable. What this is saying is that the only pieces that will get affected if I do an alpha move and then a beta move, and then the inverses of them, alpha inverse, beta inverse, the only pieces that will get affected are the pieces that are in that intersecting green blob. So that is all the positions that are affected by both alpha and beta. So those are these three positions here, these two corners and this edge. What else do we have? Well, let's think about a piece that's, like down here. Let's think about that piece. So see if I can hold it, sort of looking in one spot and trying to hold it and turn it in another spot. So this is my my yellow face is my beta move, my blue face is my alpha move. So I'm thinking about something that's not being affected by either in some sense. So what happens? When I do an alpha move, and then a beta move, and then an alpha inverse move, and a beta inverse move, that piece never got touched at all. So it just stays where it is. And that's just meaning that in our diagram, there are also other pieces on the puzzle that don't get touched by alpha or beta. So they're going to remain fixed in the end. So now let's go back to, what about the pieces that alpha moves but don't get moved into spot where beta moves them? So say this corner up here. This corner, when I do the alpha move, it's now up here. So hold my finger on it. And then I do the beta move. And then I do the alpha inverse move. And then I do the beta inverse move. And so it just returned back to where it started from. And why was that? Because all it did, if we think about it, all it did was when we did the alpha move, it moved over here. And then when I do a beta move, it's not touching it at all. So then when I do the alpha beta move and then I do the alpha inverse move, it just comes back to where it started. So those are like these points here, these objects that are sitting in these other pieces. They're things that got moved by alpha, but never got moved into a position that beta also moves. And so then the last piece of this is, or the last piece, sort of no pun intended, the last idea involved in this is, what about the pieces on the intersection and the ones that move there? So alpha moves all of these pieces into the intersection. It moves, beta moves all of these pieces into the intersection, and these are the intersection pieces. So what this is telling us, that if I do the commutator of alpha, beta, alpha inverse, then I do an alpha, beta, alpha inverse, beta inverse. What ultimately ended up getting moved in the end? Well, I can see all the pieces that aren't in their original spots just by looking at colors. It's all of these pieces, all of these pieces, and all of these pieces. And those are those three green blobs. It's the intersection, all the pieces that alpha move to the intersection, and all the pieces that beta move to the intersection. And moreover, what ended up in the intersection were the pieces over here. So the pieces on that alpha side, they got moved into the intersection. Where did these ones go? The blue yellow pieces, they ended up, this one ended up there, that edge piece. And where did that orange yellow edge piece go? It ended up here. So we've got some idea of where the edge pieces went. What about the corner pieces? Well, if you look, we can see that we had a orange, white, blue corner piece. So the corner piece that was back here ended up going down here. So this corner piece ended up going there. This corner piece, which was yellow, green, and orange. Sorry, where are you? There it is. So that ended up here. So it ended up swapping these two corner pieces, and it ended up swapping these two corner pieces. So it did a 3 cycle on the edges, and it did a couple of corner swaps. And that's what we got just by doing the alpha, beta, alpha inverse. So we could predict what got moved, and we can also see where they get moved to. So that's the idea behind this picture. And again, the picture isn't quite complete because it looks like it just 3 cycles things, but we saw that the corners had like a double swap in it. So if the corners had a double swap and there was a 3 cycle of the edges, it means something more is going on in this diagram than just this nice sort of flow. And that has to do with if there's an intersection between these pieces, between these faces. And that was my overlapping diagram, where these green things, these green blobs and the one in the middle actually had a corner that was overlapping on all of them. So that means that the picture generally isn't sufficient to get a full idea of what's going on. And that's where a proof like we're about to write down here comes into play. And so what is our proof? We're going to say suppose we've got a piece that's moved by the commutator alpha beta, then what has to happen? Well, then we get these two things. The piece, or the position that the piece is in, has to be moved by alpha, or beta had to move it into a position that was moved by alpha. So that's the first line there that says, how could you have possibly been moved by the commutator? Well, you would have had to have been moved by alpha, or beta would have had to move you to a place where then alpha moved you. What about part B? Part B says, well, you could have also, this is an and, so you would have also had to have been in a place that beta moved, or in a place where alpha moved you to a place that beta moved. So and somehow you had to get mixed up in both an alpha move and a beta move in order to be moved in the end. You couldn't have just been moved by alpha and not beta, because you would have just rocked back and forth. Or you couldn't have just been moved by beta and not alpha, because you would have just rocked back and forth and ended back restarted. So somehow you had to get caught up in a mix of both the alpha and the beta moves. And this is precisely what this is saying. And so if that's the case, if these are the conditions that that we have to have on M in order to be in the move set of the commutator, then that means that the move set of the commutator is precisely the intersection of these two sets. You're either in, so I sort of wrote these in the opposite order, but this one here is that condition, and the first one's over here. So the first condition is you're either in the move set of alpha or beta inverse of the move set of alpha. And also, you're either in the move set of beta or you've been taken to the move set of beta by alpha. So you're in alpha inverse move set of beta. And so let's go ahead and prove A and B. So we're going to prove A first. And what we're going to do is we're going to prove the contrapositive. So in other words, we're going to suppose the negation of the result. So suppose M is not in the move set of alpha, and that it's not, or that beta of M is not in the move set of alpha. Then we will show that M cannot be moved by the commutator. That's what we want to show. If it's not moved by alpha and beta of M is not moved by alpha, then it couldn't have been moved by the commutator. It wouldn't have got mixed up in the two moves as they're being done. So how do we do that? Well, what we'll do is we'll just see what happens when we apply the commutator to M. So now we're thinking of this as a function, right? It's a function. M is an input. We want to know when we do this move sequence, where does the piece in position M go? Where does it end up? So first we write down what our commutator is. And then here's one key fact that we mentioned early on in the course, but worth repeating now. We read our permutations from left to right. So we think of, we're doing alpha first, then beta, then alpha inverse. So this is saying first do alpha of M, then do beta of that, then do alpha inverse of that, then do beta inverse of that. So we read our permutations from left to right. So that's what a composition is. We have to start with the leftmost function and proceed to the right. And what do we have here? Well, alpha of M. That's the first thing we're going to do to M. We're going to take alpha of it. But we note that M is not moved by alpha. In other words, M is in the fixed set of alpha. So alpha doesn't move it at all. So that means that this is equal to M. And so we've got beta inverse, alpha inverse, beta of M. And now we have to look at the next bit. So beta of m, okay, that may be some other number like k or whatever, but then what is alpha inverse of that? Well, looking at this as a whole, now m has moved to a different location. Let's move to location beta m. But beta m is not moved, sorry, this is a not, right? So we're supposed to assume not here. My apologies, I missed the not sign. So, but beta of m is not moved by alpha. And because the move set of alpha and the move set of alpha inverse are the same thing, because whatever alpha moves, the inverse also moves, they just move them in opposite directions. That means that beta of m is not moved by alpha inverse either. So I have beta of m, I apply alpha inverse to that. It doesn't move it, it stays fixed. So that's beta of m. And so this becomes beta inverse of beta of m, which is m. And therefore, the commutator, when applied to m, leaves it untouched. It doesn't move it. So m is in the fixed set of alpha beta, or in other words, m is not moved by the commutator alpha beta. And so that's the contrapositive. We wanted to show that if it was moved by the commutator, then it had to have been in either the move set of alpha or beta of m had to be in the move set of alpha. So we did the contrapositive. We assumed that it wasn't in either, and therefore it's also not in the move set of the commutator. So the commutator doesn't touch it, leaves it alone. And the similar, almost identical proof for part B. It's just, I mean, instead of doing the things with alpha and beta in the order we've done it in, we reverse the roles. Okay, so what this tells us is this is exactly what the commutator is moving. And we can write that in an analogous way. And I do this, actually, I think I have this left as an exercise, how to go from star down to this result down here. But this is another way to write star, is that the move set of alpha and beta is a subset of the move set of alpha, beta, union, the things that are moved by alpha to that common intersection and the things that beta moves to the common intersection. So that's our, back to our picture again. Okay, so that's sort of the big theory that commutators, we can predict exactly what's moved. Now, I will say that the only way you really get an understanding for this is actually to do it on puzzles. You're going to start to build these things on puzzles, you'll play around with them, and then it'll start to click into place exactly what these sets are. So you might be a little bit overwhelmed with notation right now, but that's to be expected. So let's go ahead and figure out what it says in plain language. So what this says in plain language is if you have two moves, alpha and beta, then the commutator only affects pieces that are in or moved to the locations that are moved by both alpha and beta. So I'll draw the picture again. We've got our move alpha, our moved beta. Here's the stuff in their intersection. So those are the positions that are affected by both. But the other positions that are affected are the things that alpha moves into those locations. So those would be these pieces here, and the things that alpha moves into those locations. Those are the things here. And those are precisely the only three collections of pieces that are going to get affected by the commutator. Things in the intersection and the things that move to the intersection. So let's go ahead and start creating some moves on Rubik's Cube. So I've got some pictures here, but we'll go ahead and we'll do those actually with the physical cube. So let me just scroll this up a bit so we can get it in there. Okay. So now we're just going to pick some moves and do their commutator. So we're going to start slowly, just basic moves. So X is U and Y is R. So what is our move here? X is U. So that's this move here. I'm imagining my blue as my U face. And Y is R. So this is our R move. Remember, the positive move is clockwise in the direction as you're facing that face. So if I'm staring at the right face, there's an R move, it's clockwise. If I'm staring at the up face, I'm rotated in the clockwise direction for the positive U. The inverse would be counterclockwise U, or U inverse. Okay, so let's go ahead and figure out what a commutator of U and R does. So a commutator of U and R would affect the pieces that are common to both the U and the R move. So I look at the R move and I think, okay, it moves all these pieces that are being moved right now. And the U move, it moves all of these pieces. So the intersection is precisely these three pieces: corner, edge, corner. So those three pieces are what gets moved by both of them. But the commutator also affects the pieces that get moved into those locations by both moves. What does U move into these locations? U moves these pieces. So those ones are also going to get affected. So these pieces will get affected by the commutator. The intersection will get affected by the commutator. And the pieces that R moves into those locations, those are these pieces here. So those get affected. So we immediately know that the commutator is going to affect these pieces here. 1, 2, 3 edge pieces, 1, 2, 3, 4 corner pieces. And so that's it. We know that if we do a UR move, exactly what, or the commutator of them, exactly what pieces are going to get affected. So we can go ahead and do it. U, R, U inverse. Oh, sorry, I turned R the wrong way. So let me do it again. U, R, yes, I did it the right way, clockwise R, U inverse, R inverse. And what pieces got affected? Precisely these ones here, which is what is shaded in that diagram above. We can do the inverse of the commutator by just reversing the commutator. That's an exercise for the homework assignment, that the inverse of the commutator of X and Y is just do the commutator of Y and X. And so that'll help you undo them. What else could we do? We could do an FR, so a front face and a right face. And the right face is this way, right clockwise. So F clockwise and right clockwise. This is the intersection. This is what F would bring to the intersection. This is what R would bring to the intersection. So I immediately know that doing an FR commutator will affect precisely these pieces here. And that's what that picture above shows. So we know exactly which pieces get fixed. If I wanted to affect these pieces up here and that intersection, then I just think I'm going to do 2 moves where that's the intersection. And then I'm going to make sure one of my moves brings these pieces to the intersection. The other move is going to bring these pieces to the intersection. So I'd go an F, R inverse, F inverse, R. And that has affected precisely these pieces along what looks to be like the shape of a letter Y. And so that's how we can start to build moves. So you might say, well, you still moved a lot of pieces, 4 corners and 3 edges, but we'll see in a second how we can do a little bit more with this. But I do want to point out that these ones have names. So these 2 here, they're called Z commutators because they kind of look like the letter Z, this one more so than the other one, but they kind of look like the letter Z. Whereas this one looks like the letter Y. So we call this a Y commutator. And David Singmaster, back in the early 80s, around the time the Rubik's Cube was getting to be its most popular, like 1980, 1981, in North America, David Singmaster, he was a mathematician, he developed these Z and Y commutators and gave methods for solving the puzzle just using these alone. So these turn out to be quite powerful. And you might say, well, it still moves a lot of pieces. But let's see what's happening here. When I do that commutator, which I did the very last one, the Y one, I got this edge piece, which is a blue-red one. It moved down here. Then that edge piece went up here, and this edge piece went over here. So I did a 3 cycle on the edges. I did a 3 cycle on the edges. And it also did a swap. The corners that got swapped were these two sitting in front, that corner and that corner swapped. And then these two corners swapped. So what does that mean? Well, how can I kill a 3 cycle, for example? Well, I could do it 3 times, and that would restore the edges. So let's do that. So we did an F R inverse once. So here's the second one, the commutator of F R inverse. And then I'll do it one more time. F R inverse, F inverse R. The edges have all been restored, but my corners are now out. These have been swapped. These have been swapped. We know it's impossible to do a single corner swap. That's an odd permutation, and we already had arguments about that. But this shows us how we can do a double corner swap, which is an even permutation. So we've just developed a double corner swap on the puzzle using commutators. And then we can do it again. So F R inverse, F inverse R, F R inverse, F inverse R, F R inverse, F inverse R. So I did it 3 more times for a total of 6. We get back to where we started. So that commutator has order 6. We can do it again. So F R inverse, F inverse R. And I'm just going to do it twice. F R inverse, F inverse R. So I've done the commutator twice. Why have I done it twice? Because now the corners were a swap and a swap back. What we can see has happened is this corner should be the blue, yellow, and red one. It is blue, yellow, red. It's just been rotated. And this corner is in the right location. It's green, red, yellow. It's in the right location. It's just been rotated. So all my corners are back in their original locations. They're just rotated. So if I'm just interested in putting corner pieces back into their proper spots, then this is fine. I'll deal with rotations later. So here we've got a 3 cycle on the edges. I was able to 3 cycle the edges around. They're not in their home locations, but all the other pieces are back in their home locations. Maybe not their home orientation because they've been rotated. So we can start to use this to move. I've done a 3 cycle now, if you want. Done a 3 cycle of the edge pieces. Corner pieces are back to where they started from with the orientation issue, which we deal with in other ways. So now we're starting to get a feel for how to build these things. Now let's go ahead and look at some other ones. So these are the fun ones where things really start to happen. So let's consider this first move X, which is L d squared L inverse. And then I'm going to take the commutator with U. So what does L d squared L inverse do? So let's have a look. We're going to do an L d squared L inverse. Okay, so what it did was it affected a lot of stuff, but if I'm going to just take the commutator with U, then all I really care about at this point is what's going on in the intersection of this move and U. And it's only that piece there that's going to be in the intersection of the X move and the Y move. So it's that location, that's the intersection. So if I do a commutator of X with a U move, so with a U move, then the only pieces that are going to get affected are the pieces that are in this location, the intersection, the piece that U brings to that intersection, which would be this piece here, and the piece that the first move X brought to the intersection. That's this piece, orange, green, and yellow. And it's actually that piece that was way back in the back corner here. So let's just see why is that the case. So this is my first move. I bring this piece down. That's my L move. Then I spin the down layer twice. Maybe I'll spin it the other way just so you can see. So this corner in the back, it's now coming around and sliding into place. And then I'm putting it up top. So all I did was brought this corner piece up here. And I know that if I do the commutator of this with U, it's only going to affect this piece, and that piece. So I'll do the U and then inverse that L d squared L inverse by doing that, and then undo the U move. And we've undone the U move. And now we see it's only affected those 3 pieces. So we've now got an ability to cycle 3 corners. I'll do it again. L, D squared, L inverse. That's the first move. U, L, D squared, L inverse. Undo U. So we've done it again, and we've just cycled them one more click. If I do it one more time, L, D squared, L inverse, U, L, D squared, L inverse, U inverse. We're back to where we started. So we've just built a 3 cycle on the corners. And we've done it by using the idea of a commutator. Find 2 moves that have a small intersection. In this case, the intersection was only 1 corner. And figure out what each of those moves brings to that corner, and then you can predict exactly what happens. I'm 1 minute over. But what I want to do is I want to give you this last one here. And then next day we'll go on to the oval track and build some moves there. But I want to show you how to do the corner cycles, 3 cycles, sorry, the corner rotations as well. So this is going to be a move where we can rotate the corner pieces in place. And you see this long sequence. I say do an X move, which is L, D squared, L inverse, F inverse, D squared, F. Okay, it's not so much a matter of memorizing what that does or that move sequence. It's a matter of just figuring out what is it you want to do. So what do I want to do? What I want to do is I want to take this corner piece and I want to run it around the puzzle and bring it back up, rotate it. So what I'll do is I'll imagine there's 2 elevators that allow me to get up here. There is a left elevator that allows me to pick pieces from down here and bring them up into that location. And there's a front elevator that allows me to pick a piece up from here and bring it up into that location. So I can use the front elevator or the left elevator. And so what I'll do is I'll take the piece that's standing here and I'll let them ride down the elevator. They will get off, but I want to make sure that they get off completely from the left elevator and the right one. So to get off, I have to make sure I'm not on the front face either. So I'm going to do a D squared to hide all the way in the back. So a place that's not on either. Then I'll send that elevator back up again. And then I'll bring the front elevator down and pick that piece up. So doing a D squared move to pick it up and then bringing it upstairs. And so that was a move that just rotated that 1 corner. And you may say, well, it messed everything else up. Yep, it did, but that's nothing I need to worry about, because if I do the commutator now of this move I just did with an up move, then what's going to get affected? It's the piece that's in the intersection. So it's this piece, which is in the intersection of the up move and the one I just did. And what got moved to that intersection? Well, the first move didn't move anything new here. It's still the same piece. The second move is going to bring this piece into the intersection. So if I do the commutator of this move I just did, it'll only affect this piece and this piece, because that's the piece the U move is going to bring there. So I'll bring the U move there, and then I'll undo the sequence that brought that twisted that first corner. So I just have to remember I brought it down with the left face and then up with the front face elevator. So I'm going to do the opposite. Bring it down with the front face elevator, hide it, restore the front face elevator, bring the left face elevator down, load it up, bring that left face elevator up. So now I just undid the X. So I'm at the X, Y, X inverse part. Now I have to do the Y inverse. And that's now built. 2 corner twists where I twisted them in opposite directions. And so now we can start to build moves. Now I know how to twist 2 corners. I know how to cycle 3 corners as well. We just built that one. So we're now starting to see how we can build puzzle moves on the Rubik's Cube using commutators. So that's it for today. We'll finish the oval track next day, and then we will get into conjugation. And conjugation is how to modify existing puzzle moves. We're now learning how to build them, then we'll learn how to modify them.